A very good afternoon to everyone. So we wanted to discuss the energy and intensity of a string wave. This is a very important concept. Let us consider over here this y equal to a sine kx minus omega t to be the traveling string wave over here, and we want to find out the first of all the kinetic energy of a particle. Now we notice that there is the wave which is moving to the right side over here, as can be seen, right? And therefore we are considering over here a particle. If you notice over here, then at this particular location, which is the peak point, whatever is the length of this particular portion over here, right, this region, the same amount of length will be present over here also, right? And the kinetic energy at the extreme position, it will be zero itself, whereas the kinetic energy of the particle at the mean position will be maximum, correct? Now let us consider the small amount of element which is located at this particular position over here. Let this be the x coordinate over here, right? And a small amount of dx, an increase in that, this particular quantity is nothing but the dm value, which is equal to mu times of dx, right? So therefore, now how much is the value of dk, the small kinetic energy of this particle? It is nothing but half of this dm multiplied by vp square itself, right? Vp is nothing but dou y by dou t, which is the rate at which the y coordinate of this particle changes over here, right? So once you differentiate this y, you'll be getting this particular expression. You square it over here, and we get the value of dk as half mu dx into this vp square itself, right? You shift the terms over here, and you get this a half mu into omega square into cos square of kx minus omega t into dx, right? This is the kinetic energy of a small element of this string. Now what about potential energy? You can see that the dx over here at the topmost point, whatever is this length, will be the same as this length over here, right? But we notice that a particle which is at the extreme position of this dx length over here, as the string wave will move, now this dx will no longer be, the length of this element will be no longer dx, it will be slightly more over here, that is nothing but dl. So therefore at the extreme position, if the length of that element is nothing but equal to dx, and this portion over here will not be equal to dx, it will be equal to dl value, right? The same thing we have considered on this right side over here, right? So therefore, now what has happened to this particular elemental length of dx? It is now elongated, right? What should have been only this particular dx amount is now elongated to this particular larger amount of dl over here, right? So who has elongated it? This is nothing but done by the tension force of the string itself. So the work done by the tension force in elongating the string from dx to dl is nothing but getting stored as the potential energy, similar to how the work done by the external force causes an extension in the spring, and whatever is the work done is getting stored over here in that spring as the spring's potential energy, in the same way over here. So work done by the tension force in stretching the length of the element from dx to dl is nothing but equal to this value of du itself, the potential energy which is stored. How much is that? It is nothing but the force of tension multiplied by the extension over here, which is dl minus dx. पहले वो dx था, अब वो dl हो गया, extend हो गया. Now we can always say that this dl quantity over here can be written as this dx and this dy. In terms of these two we can write, where dy represents the small amount of increase in the value of y, right? So therefore you substitute over here the value of this dy as root of dy square plus dx the whole square, and now you pull out the dx outside over here from these two terms as a whole, in this one as well as in this one. So therefore over here we will be getting, if you take dx as common, then the inside quantity will be root of 1 plus dy by dx the whole square, and this dx is also removed over here, taken as common over here, right? So therefore we observe that now let us substitute the value of this dy by dx. Before that, these are very small displacements, correct? Yes, the amplitude are very small, which means that the slope quantity over here, that is dy by dx, will also be very small over here. Since the amplitudes are very small, therefore tan theta is a negligible value, dy by dx is a negligible value compared to 1. So therefore we apply over here the binomial approximation. 1 plus x the whole power n is nothing but 1 plus n times of x, where n is nothing but 1 by 2, right? Minus 1 plus 1, that will get cancelled over here, and you will only be having this half of dy by dx the whole square, half of mu v square into this term over here. Now how much is the value of dy by dx? That means the slope at this instant of time. At this instant of time we are going to treat the t as a constant. So therefore replacing dy by dx as equal to dou y divided by dou x, we now replace this value from y equal to a sine of kx minus omega t. We find the dou y by dou x quantity, and we substitute over here in this term, and over here we get this expression mu v square half into dx dou y by dou x. You notice that it is there is one so why did we write this 1 by 2? That 1 by 2 should not be there over here. It is just ak cos of kx minus omega t, right? Now substituting this particular value, we get this expression over here, right? So therefore now what is the product of omega square and k square if omega by k is nothing but equal to v, which means vk is nothing but equal to omega. So you replace over here this particular v square times of k square as equal to omega square, right? And the remaining terms are mu into a square into cos square into this dx quantity itself. So therefore if you just compare this du term, which has half mu a square omega square cos square dx, with the decay term that we got earlier, half mu a square omega square cos square into dx, they are both the same. So the kinetic energy and the potential energy are the same for an element, for a traveling string wave element. Potential energy per unit length and kinetic energy per unit length are the same. And where is it, what is the total energy? Sum, the sum over here. So the total energy over here is a sum of the du and the dk for that particular element over here, right? So therefore we observe that if this is true, then what about the total energy? This is only for one particle, please make a note, right? It doesn't mean that the total energy will remain a constant value for that element. No, as the element over here reaches the extreme position, the kinetic energy will become 0. The potential energy also becomes equal to 0 because it is equal to the kinetic energy. And once it reaches the mean position, the potential energy will be maximum. The kinetic energy will also be maximum because the speed of the particle is maximum. Does it mean that all particles are at the same mean position at the same time? No. Different particles, some of them will be at extreme, some of them will be at mean. What is the total energy of one wavelength? That we want to find now. To find out the total energy, we will simply do integration over a wavelength. So therefore, integral of dE, integrate this term from 0 to lambda. That's all. You get this particular expression over here, right? This part is clear, gentlemen. No, the kinetic energy for one wavelength is the same as the potential energy for one wavelength, and the sum of the kinetic energy and the potential energy, they are also equal to the total energy. So 1/4 you'll be getting over here, right? This part is clear, no doubts are there. Okay, moving on to intensity. Intensity is nothing but the amount of energy crossing a section per unit time, per unit area, in a direction perpendicular to the area. So which is power by cross-sectional area, which is energy by time per unit area. I will remember the density is mass by volume. Volume is the length into the area S. So rho into S is nothing but m by L, this term over here. And therefore, what is the value of this mu? Mu is m by L, which is rho into S. We will remember this particular expression. So let us substitute this over here in the energy per unit time. We notice that the wavelength divided by time, because in the energy expression you have this term of wavelength over here, right? So once you substitute, you divide by this time quantity, you will be getting lambda by time. Lambda by time is nothing but the wave velocity itself, which is your v. And you get over here half mu into a square into omega square into lambda by t, which is v, into 1 by s. Now what is mu by s over here? This mu divided by this s over here. What is that? That is your rho itself. This is the expression for the intensity itself. Half rho a square omega square into v. This part is clear, gentlemen. No doubts are there. Yes? Excellent.